Welcome everybody to today's Heidelberg Joint Astronomical Colloquium. Today we have a visitor from a long way away, Alexander Heger, and to introduce him, I'm going to hand over to his host.
Thanks a lot, Richard. Yeah, it's a pleasure to welcome Professor Alexander Heger from Monash University in Australia to Heidelberg. Fortunately, he's in Germany for the current time, so we didn't have to fly him over all the way, and he just had to take a train ticket. But yeah, let me introduce you a bit to Alex's careers, which of course started in Germany, actually at the Technical University of Munich, where you did your diploma thesis on something very familiar to me, actually, namely stationary models for Wolf-Rayet stars with optically thick winds. Yeah, so there's some interest that go way back. You did that at that time with Norbert Lange, and then also did your PhD at the Max Planck Institute for Astrophysics in Garching about the pre-supernova evolution of rotating massive stars, where you got in contact with Stan Woosley, who then was your host for a Theodor Leinen Fellowship for a postdoc for 3 years at the University of California at Santa Cruz. Then Alex went to the University of Chicago as a postdoctoral fellow at the Enrico Fermi Institute before becoming a staff member in the theoretical astrophysics group at Los Alamos National Laboratory. And then finally becoming an associate professor at the University of Minnesota in 2008, before moving to Australia, now having been since then at Monash University. So since 2012, you have been a professor there. And you had some interesting guest visits in China, namely as a guest professor at the Jiao Tong University in Shanghai and the Tsingtao Li Institute from 2015 or 2018, respectively, until I think COVID, essentially, right? 2020. So with this interesting career and all stages of massive star evolution, I'm taking over to Alex to tell us about finding actually the oldest star and what that has to do with massive stars.
Thank you. So yeah, usually what I'm working on is we're looking at the first star set ever formed, but the question that comes also out when we look in our own galaxy, where might we be able to find what is left over from this first generation and what is even left over from as early back as possible, which inspired me to this unusual title, Finding the Oldest Star in the Galaxy. And I first prepared this talk a little bit less than a year ago, and then we had a very, we thought we found it, but at the end I will show you that maybe we didn't. And so there's still a prize to be won. I will get to that at the very end. Okay, so a dated picture. So where do stars form? And they form in molecular clouds. So in the upper panel, this is how in the optical, the Radius regions looks like, but this is how it looks like in the infrared, where you see inside that cloud. You can't see an optical light, you can see the infrared, so it happens deep inside the clouds. You start forming stars. And then once you form a star, you can basically describe its evolution as this gas cloud contracting to ever increasing central densities. So central densities down here for central densities, and ever increasing central temperatures shown here on the y-axis. So that's the overall picture. If a gas cloud, it contracts, and that's sort of the evolution of a star. Of course, there's a little bit different paths that can occur depending on what the mass of the star is, and that relates to some microphysics. One has to understand whether, for example, electron degeneracy starts playing a role, whether it's relativistic or non-relativistic. Then you can have some nuclear physics playing a role, that if your electrons are very degenerate or have very high Fermi energies for the degeneracy, then you can capture them on nuclei. And there's other things, when the temperature in your gas gets hot enough, you can make electron-positron pairs, and they take out energy of your gas and convert into rest mass of matter. So that takes out energy. So this indicates then these red stripes here, instability. Or if the gas gets extremely hot, you can even disintegrate nuclei, but and since nuclei are very tightly bound, that costs you also a lot of energy, leading to instability. And then you have these different outcomes where you can have either here down white dwarfs or some kind of supernovae, different kinds of supernovae, or maybe it collapses instead. There's another kind of supernova I will get to. Or you make black holes. So they get explosions, and maybe in some cases, depending on the details, you don't get explosions. And it's of course a very wide range from like a few solar masses to millions of solar masses or so. So that's not, yep. This one or previous one? Because of this stuff here, degeneracy. So because in order to make electrons, you need a space for them to go. But if your gas is electron degenerate, then you have to create them at a minimum Fermi level, and so that gives us a problem because then it costs you extra energy. That can suppress it. It's also densities are higher, and so they would annihilate faster, and so you don't maybe make a sufficiently large abundance. But there can be two things. There can be this Fermi blocking of production of pairs, as well as that the time scale for them to annihilate can get shorter because you have higher electron density. Or the positrons to annihilate again. Yeah. But yes, yeah, that's constrained to that side because of physics. Yeah. So beyond this overall picture of generally contracting, I showed you the path of two of these stars for a 15 and a 25 solar mass star. And the stars actually, while this overall picture is continuously contracting, but it actually takes a rest every now and then. For example, it stops here at hydrogen burning, where it spends about 90% of its lifetime. And then there's the next time it stops is a helium burning, and where it spends almost all of the rest of its remaining lifetime. So like for massive stars, it can be a few million years. For the sun, this takes 10 billion years. And this one takes typically 10% of the time. And so during these stages, you just have a state where the star loses energy from the surface. And at the same time, it's that this energy loss from the surface that we always have is balanced by the nuclear energy generation that occurs in the center. And then everything gets more or less stationary in terms of the energy balance. It changes a little bit, as we will see when you get to carbon burning, oxygen burning, silicon burning, because at this point the stars get so hot that they also make electron-positron pairs in their center. And then the star starts shining mostly in neutrinos and no longer in photons. And so they become really, from that point on, basically neutrino stars. And the time scale then significantly accelerates, and this is why it goes so fast. So the energy that's released in helium burning is about the same as in carbon, oxygen, silicon burning, but it's just that the star no longer loses it just from the surface in terms of photons, but it loses almost all of this energy from the center in form of, sorry, you don't lose it just from photons from the surface, but you lose it from neutrinos at that stage. And so that's what makes things then go very fast. We'll see the next slide. So here a summary. We probably don't have time to go through all of it, but it shows you again that it's not only the sequence that we see, but there's also recycling. So since it's very fashionable these days, so stars do that very efficiently, that they produce one ash, and the ash is the fuel of the next stage, and that continues a few times. Here show you also the key reactions. So this is the case for 20 solar mass star. Hydrogen burns the helium at about 20 to 30 million Kelvin. It takes 10 million years. Mostly by converting for hydrogen 1 helium-4 in different ways. For this massive star is something called the CNO cycle doing it. And you make a secondary product is nitrogen-14, which is interesting. So everything that initially was carbon, oxygen, nitrogen in that cycle ends up almost all of it as nitrogen-14, which is then important later on. Then the next stage was this helium burning that makes carbon and oxygen, but it also converts your nitrogen-14 into oxygen-18 and neon-22. And this neon-22 in the end can undergo another reaction that releases neutrons. that can drive various nucleosynthesis processes. So the time scale is now about, or the temperature is about 10 times higher, the time scale is 10 times shorter. And the difference here is really because this second process releases 10 times less energy of the order. And so there's two different reactions that compete with each other and determine how much oxygen and carbon you make respectively. And this is a very important debate going on in the current literature and for studying what how many neutron stars and black holes you make is getting correct, what the ratio outcome is, because it affects later evolution. Then the next stage, I said, is carbon burning, makes neomagnesium, and also a little bit of sodium, release a few more neutrons. Temperature is around a billion Kelvin, a little bit below, but the time scale is now a factor 1,000 shorter because you lose all of the energy in form of neutrinos. And it's dominated by that reaction. And then next is not the oxygen, but it is in between something else, neon burning, because it burns in a very peculiar way where you have a hot, high energy photon coming in, kicking out an alpha particle, making oxygen, and that alpha reacts onward with some neon to make magnesium-24. And so this one makes magnesium and some other side effects, aluminum, phosphorus, maybe 1.5 billion Kelvin. And the time scale is now of the order of years. Again, the temperature is higher, and therefore you make neutrinos much more efficiently, making this time scale short. But you don't also usually have a lot of neon in there. The next is then oxygen burning, silicon and sulfur, and you make some side products from that reaction from oxygen plus oxygen 16. Yeah, and temperatures is 2.5 billion Kelvin, and the time scale in this case is not that much shorter. That's mostly because you tend to have a lot of oxygen, and there's probably something like 80% oxygen at this stage. And so it lasts maybe a fraction of a year. And then finally, you have silicon and sulfur burning, making iron and other iron group elements at maybe 3.5 billion Kelvin. And that now lasts 0.02 years. So that's a week. So, things go really very fast at the end. And at that point, towards the very end, the star also becomes about 10 billion times brighter in neutrinos than it's visible at the surface. And this is where we have some hope if one of these things is very close by and within the last few days before it dies, maybe a sufficiently large neutrino detector can see the closest by stars when they get into this phase. And then we would have a warning signal where to point our telescopes. So for Betelgeuse, people were hoping that and as the detectors get better, we're getting closer to being able to do this. Okay. The next I want to show you is how does all of these different phases actually look like inside the star. And what I show here is a 22 solar mass star initially. So we have here is what we call the mass coordinate. The idea is the star is mostly round, and therefore we make spherical shells. And for each of the shells, we can say how much mass is inside. And so tagging something by mass is very useful. We call this Lagrangian coordinate because it tracks the composition of things. So we know on a certain mass shell, unless there's some mixing in between, we know that the composition doesn't change on these shells, whereas the star can expand and contract by many orders of magnitude during its lifetime. And the shells move in and out by quite a bit because density gets a lot higher. But this way allows us to track these mass elements. And then I have here on the x-axis, I have time since we're doing astronomy, we always do this in a weird way. So this is in reverse order. So it's this time until core collapse. The time goes in this way, but I do the logarithm of the time in years until the final death, which is here at about 1/4 of a second, where the plot ends before the star finally collapses to a neutron star, a proto-neutron star. And so it's 1 second before, this is 1 year before, this is 1 million years before. And so yeah, this curve is the total mass, so the star loses mass over time. In this case, it's for solar metallicity star. So there's a mass blown off from the surface, and yeah, the slope of the curve should not be misleading towards thinking, oh, there's not a lot of mass lost at the end. That's not true because the time scale is logarithmic, so it's actually very little mass loss at the beginning, and then it gets very fast at the end. But of course, it's stretched out because of the axis choice. And so then we show where energy is produced, and this is in this blue shading. So each level of or shade of blue is 1 order of magnitude more energy generation rate, and it's energy generation rate per unit mass, so specific energy generation rate. So that the area that you see here is actually representative of the energy that is being made. And so basically you see it's usually always very much concentrated in here because it's 10 times higher than in that region, but it's more than 10% of the area. So that's almost all is happening here at the bottom. And we see these different phases, and we'll come back to them, what these different things actually are that you see. The next thing is the neutrino losses. So actually, I did not plot just the neutrino losses. I plot the net result of energy produced minus what is being carried away by neutrinos. And towards the end, this entire core is very hot, so it loses lots of neutrinos, but except for some regions where the burning dominates over the losses. The next important point is to put in convection. And so convection is kind of like you put a pot of water on the stove where you heat up a soup. And since you input all the heat at the bottom, which is what the stars also do because they have all of the energy generation at the bottom, and then this convection, what it transports the heat out, but it also keeps the thing well stirred. So when you have your noodle soup cooking very well, then all the noodles and pasta and the chicken, whatever you have in there, is all very well mixed. And this is also what the stars do. So let's keep this in mind. This is energy transport, and mixing at the same time is what convection is doing. And then there's different kind of physics happening that at some point this stops, and we have here very small zones. I put lines around them, so this is just many of these small zones, but you only see the boundaries. In the outer layers, the star becomes opaque enough that the radiation can just get out. You don't have to worry, as you no longer require convection. Okay, next there's something else called semi-convection. It's a smaller mixing process. We don't have to look at it in too much detail. And so this is now the full picture. What we have is we have this first phase of core hydrogen burning. You remember everything is well mixed. So that also means that this burning, it depletes hydrogen, but it's in the entire mixed region at the same time. And then after that, so we have here no more hydrogen, but the hydrogen continues burning in a shell. Then we have here in the core helium burning, the same thing happens. You deplete helium more or less at the same time in this entire convective region, and then you continue helium burning in a shell. Then we have carbon burning. In this case, it didn't burn convectively at the beginning, so it burns outward, and then eventually becomes convective and drives a shell in another shell. Then we have neon burning. This is these very small shells here, a whole sequence of them. And then we have oxygen burning in the core and in some shells, and then silicon burning in the core and in some shells. And then we would have built up eventually an iron core that is big enough that it exceeds some critical mass, something related to the Chandrasekhar mass you may have heard of, and then it collapses and you get a supernova explosion. I also skipped over outside. That star becomes a red giant in this case of simulation, so it has a huge convective envelope, and the star here would be something like 1,000 solar radii at this stage, whereas initially it may be 10 or less solar radii. So, okay, what happens during this collapse? So there's something very interesting is happening. That's when we look at these shells, there's a lot of energy being produced, and the convection in there can go actually quite fast, and it can have a significant fraction of the Mach numbers. And so that means that once the material is starting to fall in, because of the rapid motions, there will also be corresponding fluctuations in density because of the dynamic pressure of the motions. And so that can seed asymmetries. So that when your supernova explodes, this is from a calculation from Bernhard Müller. So you also get asymmetric supernova explosion at the end. So this shows you a little bit of the convection. But just before it collapses, where we had here some in a ring. So Bernhard actually had a simulation. This is to do the geometry was kind of a half thing shape that were matched together. This shows only one half of it, but you can see in this case surfaces of equal entropy, and you see there's a lot of convective motion before the star finally dies. And then we have an explosion, and then this is how it really looks like. So from a simulation, not my 1D version of it, where we can get asymmetric explosions. In this case, it was for a 40 solar mass star, and it's about half a second into the explosion. It's just one example. There's many groups in the world who do such simulations. Should move on it. Okay. This is a very, very crude picture, the cartoon version of how we think the outcomes of stellar evolution look like as a function of initial mass. So now we looked at one of the cases that was around here before. Now let's look at the big picture. And what I show here is as a function of initial mass of the star. So from few solar masses to 100 solar masses, I show here the kind of typical structures inside the star, both on a logarithmic scale. And so this curve here shows what the mass of the star would be at the kind of final stage that leads to formation of the remnant. And the red curve as key part is what the remnant mass actually should be. And so at the very low mass end, we make carbon oxygen, neon magnesium oxygen white dwarfs, and the asymptotic giant branch phase that makes a planetary nebula for connoisseurs that you have probably seen nice pictures of. And there's pulses going on, and you blow off this outer layer, and then eventually you have a white dwarf left behind. Then for the case that we just looked at, this normal massive stars, we have the inner part is collapsing, and you drive this explosion, and you check the outer layers. And so this can eject the helium core and even some of the metals. And this is where many of the heavy material is being produced, is being ejected from supernova explosions. And then if you go out to higher masses, something can happen is that this engine that drives your explosion, at least the standard engines for non-rotating stars, has only a finite amount of energy that you can deposit. And you may be able to initially push out the material towards an explosion, but you might not have enough energy to push it all to infinity. And then some of it is falling back onto this central object. And if it exceeds some critical value, the maximum mass of this neutron stars can have, then you naturally end up with a black hole being formed. So that's this idea. There's also a lot of things to be said up here, but Andreas Sander is one of the experts on how this is all working. So he would probably be more qualified telling you what exactly should be happening here. But the basic idea is that the mass loss gets increasingly more, and you may actually end up with the more massive stars ending up with less mass at the end of the evolution than some lower mass stars. And that there's some critical points where you, for example, remove all the hydrogen envelope, and then the star becomes a different observable spectral type called Wolf-Rayet stars, and they can have different kinds, whether you just see nitrogen that comes from was made in the hydrogen burning we discussed at the beginning, or you start making carbon and uncover some of those layers, or if it's more advanced, you may be uncovering oxygen. So these are WNE for nitrogen, WC carbon-rich, and WO oxygen-rich stars, and they may or may not give you faint supernovae, but definitely a different supernova type. So one distinguishes typically type 2 supernovae that have hydrogen envelopes, and then type 1 supernovae, 1 BCs from these massive stars that have no hydrogen in their spectra being seen. So it's merely spectroscopical definition. Okay, this is the nice cartoon picture. The real thing looks more like this, as or there's another ingredient is that the evolution is not just smoothly changing along as you increase the mass, but instead you see here lots of discontinuous and some region around here where there is things moving up and down quite a bit, and looks very chaotic. And then there's some regions where there's things, the different core masses seem to be going up and then going back down again. So this is the initial mass, and this was various kinds of core masses plotted. And there's lots of things going up and down and being chaotic here. And you can actually understand it because we saw this picture before of these convection zones, and it is all of these different convection zones that can happen in the evolution that can trigger that you have changes in how things come out. For example, you need a certain minimum mass to ignite oxygen burning in the oxygen in the core, but the number of carbon shells that you have before depends on how much carbon you have. And sometimes you have not made enough carbon, or the carbon core is not big enough to make the oxygen core, and you make another full shell of carbon burning, but that pushes you very discontinuously to a much bigger core, because the number of shells of burning is obviously an integer number, and when you flip from 2 to 3 or something, then you get the discontinuous changes, and this is what we see reflected. So all of this complicated convective structure in stars reflects in that you don't have just a smooth change in the outcomes. Let's go in, and particularly interesting here is like this bump here, for example, is the oxygen. It's an oxygen shell that sets the inner boundary of the silicon core, the Paris outcome. And this then reflects in what comes out. This was a kind of old criterion that was used to determine whether things explode or not. More important is just focus on the initial mass of the objects on the x-axis and the color coding, telling you, okay, whether there was explosion or directly formation of a black hole, or maybe a explosion that first started in blue and then somehow was unsuccessful and collapsed back to make a black hole. So you see, this is not just dividing lines where you say on this side we make neutron stars, and on that side we make black holes, and it's very easy. But instead, because of this variation of the structure as a function of initial mass, you actually can have some regions where you make black holes, and then some regions where, again, you make explosions that give you neutron stars. So it's not just one line. And there's even some of these kind of weird-looking things where maybe under some circumstances, the criterion that was used here at least predicts that even for some lower objects, the supernova explosion may not always be successful, and instead you end up possibly with some black holes there. So that's a very important message to take out. This is not it's not as easy of saying, okay, there's neutron stars on this side and black holes on the other side. Yeah. For the smallest possible neutron star mass, well, yeah, there would be down here, so it's not in this plot. So there is some things at the lowest mass end. You can do simulations at the low mass end. You get very neutron rich in the core, and so it would be around 1.2 solar masses that we can realistically get from the evolution models. So the equation of state may allow you to make even smaller neutron stars, but there is no good astrophysical pathway towards it. And from the evolution path, so you need a certain size of the core and deficiency in neutrons, so deficiency in electrons, in order for the equation of state become unstable and the objects to collapse to make a neutron star. And then you can, depending on the equation of state, you lose more or less. Binding energy is different, so you lose more or less mass, but it's slightly short of probably 1.2 solar masses that you can, at least from normal stellar evolution pathways, it's very hard to make anything smaller than that, because the objects that you realistically can get would not be collapsing. Maybe there's some other pathways that one can think of. I mean, Fritz is working on some electron capture supernovae, so possibly if you have some things that explode in very weird ways, that they eject more mass during the explosion. But yeah, he's shaking his head, so probably not. This, but from the normal assumptions, how big an object you have to get and how neutron poor it was, from that the outcome would be about 1.2 solar masses, or slightly below that. So okay, now we want to go. So this is basically the introductory part. Now we want to go into, how am I doing on time? Not sure. Okay, so should be good. Okay, so this is how things change when we no longer have mass loss. So the basic idea is that the evolution is mostly that affects these heavier objects is dominated by assuming you have no mass loss when you go to stars that are not solar metallicity. So the first slide I had shown was for solar metallicity, where twins from the surface, but for zero metallicity stars, the assumption is that usually there's not a very efficient in losing mass from the surface. So this final mass would be equal to the initial mass at the time when you reach this final phase that makes the remnants. And so this lower part would probably not change a lot, because these things can self-enrich in carbon, make carbon-rich dust, and you blow off the outer layers. And for the neutron stars, the hydrogen envelope is usually not very tightly bound, so it makes not a lot of difference for those things as well. But then as you go up in mass, it does change it, because you no longer reduce the mass of your final object, but it continues to be increasing. And eventually you get to some point where you reach this regime that Hans Günther has been asking about, this electron-positron pair instability. So somewhere around 80, 90 solar masses, the stars reach towards the end of their life this domain where you encounter this electron-positron pair instability, which means that what happens is that you have your star and you do a stability analysis, say, okay, what happens if I compress the star? So you compress the star. The one thing that happens, okay, the thing is more compact, and therefore gravity will be larger. The other thing happens because if you adiabatically or very quickly compress your gas, the pressure will go up. But there's a critical value how much your pressure has to increase in order to overcome the larger gravity that you have. And it, for the experts, that's an adiabatic index of 4/3. But if now, after the compression, the equation of state is such that, well, you convert some of this energy into the rest mass of the electron-positron pairs, the pressure doesn't rise enough. And so that means that after you compress it, the gravity wins and it contracts more, and you get a runaway, an instability. So that's a dynamical instability occurring. And that starts happening somewhere in this mass regime. But as the material contracts, also temperature rises up and you have nuclear burning, and this burning inputs energy again. And this energy can help you to eventually stop that contraction, turn it around, and lead to a rapid expansion. And initially, the energy that you get in this expansion is enough to eject the outer layers, which is why this thing here goes down. And if you don't lose enough energy, this process can repeat a few times until your core gets below the minimum value you need to drive these pulses. So it's related to the size of your hydrogen-free core, and this can drop in here, and then it can stop, and then you behave similar to these lower mass objects you call and have an explosion and maybe make a black hole coming out. But then at some point, the instability is so large that the contraction is big enough that when the burning occurs, it produces so much energy that it overshoots and disrupts the entire star. And this is what we call a full pair instability supernovae, so pair instability from the equation of state part. And so below that is pulsational pair instability, and you have a full pair instability also means that you disrupt the entire star. There's no remnant left whatsoever, and all this oxygen, carbon, silicon, whatever it made, everything of that is ejected, 100 solar masses or more. And so there's a quite dramatic change between more or less getting nothing or a weak thing, collapse to a black hole, and then having an explosion. But then at some point, when your mass gets even higher, so maybe around 150 solar masses, you actually encounter this other stripe that we discussed, instability, the photodisintegration instability at high masses, where you this very hot gas disassembles the nuclei again into alpha particles, and eventually the alpha particles into individual nucleons. And especially this part where you disassemble even this helium nucleus into free nucleons takes out so much energy that you no longer get an explosion. And you remember that this is where the star spent 90% of its life fusing nucleons together to make helium, and this is where most of the nuclear burning energy came from. And now you take this all back out again, and that leads to this second instability that within a very small range of masses. In my simulations, I try to resolve it to hundredths of a solar mass. You either get a very powerful explosion or you get nothing at all. The thing just collapses and makes a black hole. Yeah, so this is the picture we have for this very first generation. If you don't lose enough mass, you get these different kinds of supernovae. I have here a slide, but we probably won't go to all of the details. We focus on comparing a 20 solar mass and a 200 solar mass star. And the key point is that, yes, we had this time scales we have seen, but for this 200 solar mass star that encounters the pair instability, so it lives a little bit shorter. Carbon burning already gets quite fast because it's hotter as a bigger star, but then it encounters this dynamical collapse where everything happens in a few minutes, that it collapses and does burning, and then it would explode down here. So that's the interesting cell evolution input. The next question is, if you want to know what actually comes out from stars, is what stars do it actually form? And this is an interesting time evolution of what we assumed typical masses of stars for the initial mass function. So what stars do you make? What mass ranges do you make for the first generation of stars? And I missed to say here, this is for the population-free stars. And there have been some early simulations where people looked at the star formation of the first generation of stars. So these are cosmological simulations where you have some dark matter halo that contract, and then gas collects up in these halos and eventually makes the first generation of stars. And the simulations at the time told them that typically you would make stars around 100 solar masses. So had gas clouds that had 1,000 solar masses, and they were good astronomers. They would say, well, about 10% of that goes into a star, and so I make a 100 solar mass star typically. And so Tom Abel at the time told me, well, this is how these things look like. They all look like the same, and I will never have to make any more simulations of this because this is how it looks. This is how it is until you had this monolithic cloud, and it would contract to make your star. But eventually, people were able to write new hydrocodes that had significantly higher resolution. So all of this seemed very well converged within the domain, what they could do simulations, but eventually they were able to drive the resolution even a lot higher. And then it turns out there was actually fragmentation on smaller scales. And then came the prediction that, yes, you could also make much smaller stars all the way down here. This is all truncated at 0.8 solar masses. And I'll come back to that. But yes, there were, from that times on, once you had the physics resolved to an entirely new level, the outcome also was that you could possibly make something else. They still predict that maybe you make big stars, and some simulations that made different compromises between simulating large domains and resolving things had maybe higher values, or they had a larger domain, so they found more of these big objects, but they then stopped the simulation. So then the 0.1, this 0.8 solar mass truncation here, I think has an interesting, is actually, background is inspired by observations, because a star that has 0.8 times the mass of the sun, it can live as long as the age of the universe. And so any kind of population star that was made out of material from the Big Bang that had 0.8 solar masses or less, they would still be around. And we have never found one. So we have never seen one of them. So this is observationally, we think they may not have formed, not from directly simulations. So that's what we wouldn't be looking for. So what actually are the oldest stars in our galaxy? But so far, nobody has found one that was made from material directly out of the Big Bang. So how big stars can we make? Okay, in our galaxy, we see some big stars that may be up to 100 solar masses. There's one example in the cluster R136. Another one, a famous one, is Eta Carina. And that also shows a problem that we have with these big stars. Eta Carina has had here in the out. So the star itself is actually just sitting here in the very center, and this is the homunculus nebula is something that was ejected that could be of the order of a few to up to 20 solar masses that came out in a giant eruption. The big problem is that we don't know what made this kind of eruption. There's some theories, but then it's not really set in stone what really causes these eruptions. And it's a problem if you want to model such a big star and it has these gigantic eruptions where the star loses a significant fraction of their mass, and we don't understand the physics, what does that, then how can we model these stars very well? That can be an issue. Okay. So what I got at some point interested in is trying to understand what happens with all of these stars and nucleosynthesis, and can we use tools to learn more about what really was this initial mass function. So I want to make progress on that slide, saying, okay, what is the ranges and how many of each did we actually make? And so the interesting probe that we can possibly use for that is nucleosynthesis as a tracer of what was there. And so this shows you as a function of initial mass from 10 to 100 solar masses. It shows here how much of the elements do you make relative normalized. In this case, it was to magnesium, but you can normalize to whatever you like. The key thing is you see a lot of variations depending on what the initial mass of the object is. So that changes a lot. So you have some intermediate elements here at the low mass end, and there seems to be a lot rarer here at the higher mass end of stars. So you get significantly, maybe not quite unique, but sort of constraining fingerprints from each of these stellar models. So these are full stellar models. I think the database has 100-something models in it. And we also did each of them, exploded them in 10 different ways to see what the outcomes of this would be. So this is not, so this is the overall outcome from the explosions, that there's a little more that goes into it. One of the ingredients that you need to know is how much mixing happens in these stars. So we have new supernova explosions. I already showed you they are asymmetric, but there's also other hydrodynamic effects that can lead to instabilities during the explosion, in particular, mixing of the ejector with the hydrogen envelope surrounding the star. And that turns out to be very different if you look at a solar metallicity star or a population 3 star. So the solar metallicity stars have these red giant envelopes, and they lead to a lot of mixing, whereas the population 3 stars have a lot less mixing. And the mixing becomes important because something else also happens, namely this fallback mechanism. So if you have some intermediate mass star, it explodes, and then the inner part falls back, then all of that is in the interior would be lost, but not if you have mixing before, because then you have the material comes out because it's asymmetric, there's mixing with the environment, and then the inner part falls back. But if some of the material has been mixed out, then that can still escape. It will be strongly diluted relative to if just was everything pushed out, but it still makes a difference. And that also varies, for example, for a 25 solar mass star, depending on whether it's present population 1, or first generation of stars, which is called population 3. So in this case, because the star was somewhat more compact, there were a lot more material fell back. So there's the two things that happened for these POP3 stars. There is a lot less mixing, and there is a lot more fallback. So you would have a tendency for a much smaller fraction of these heavy things that are produced in the very core of the star to escape for a population 3 star compared to a star in the present day universe, in our galaxy. So the idea is, so first we have some progenitor model that has some internal structure. It's a little hard to read here. This is the initial mass coordinate that we looked at. And this is the abundance as mass fractions for different isotopes. So then we have a supernova explosion that runs through this. It does lead to some explosive burning, changing the abundances in parts quite a bit. And then finally, we assume there's some mixing and fallback happening. So assume there's a mixing that smoothes things out, and then this inner part here, flagged fallback, will disappear, and the outer part can escape. And then the picture, so the idea is, okay, there is some stars that form and we get a checker from stars. We observe these abundances, we match the abundance against the pattern, and then we get possibly can reconstruct the initial mass function of the stars. So that's the basic idea. So this was one of the interesting successes by Stefan Keller had found in the very first observations of SkyMapper. This one star, yes, very long phone number, but it had this property that there was basically no iron present or detected at only very low level. And taking this into account, so we had an explosion that was best matched by a modest explosion of a star around 40 or 50, 60 solar masses, and to match that abundance pattern. So this this one here in the comparison, the pair instability supernova didn't match that as well, because for example here calcium didn't match very well. That's an entirely different story that I could give a separate talk about, this calcium 40, but we'll skip that. So in this case, interestingly enough, it was some kind of 40 to 60 solar mass star that exploded with a low amount of mixing and with lots of fallback. So one can try more of this. This is a summer student I had. What he now tried to do is to take some of the very best studied models, abundance patterns from David Young, and compiled probability distributions and how well they match with stars of different masses, or we stack them all together in here. And so the idea is, can this possibly give you then a reconstructed initial mass function or not? That's something I should have. There's of course lots of uncertainty in this. One of these uncertainties is the different outcomes. If you, for example, have different rotation rates from non-rotating to rotating ones, the outcomes can change quite a bit. I'm going a little bit faster because we don't have the time. Okay, yeah, but I want to get some important things. So then another thing is the uncertainty in the reaction rate. For example, one of them is carbon-12 C gamma, sorry, alpha gamma reaction rate. That can change different outcomes. For example, for what core masses you get and whether you make pair instabilities or not. So there's lots of physics uncertainties that also can play a role. Okay, here show you how pair instability supernovae would look like. This was for a 150 solar mass star, where you make a little bit of nickel in the center and then have lots of oxygen come out. Or this is for comparison, a 250 solar mass star, where you have vast amount of nickel and less of the other stuff coming out. Also how the patterns look like. So you make in this lower mass, intermediate mass elements and not so much iron group, or you make lots of iron group and not so much intermediate ones. Or generally, one of the key things about pair instability supernovae is that they make an abundance pattern between the different elements that shows this big zigzag pattern. So what this shows here is a function of charge number of your elements. How much do you make of this elements relative to the solar abundances? So the solar, if this would make a perfect solar abundance pattern, all of these things would be lined up. But in this case, there's a factor of 100 different relative to the solar abundance pattern. The solar abundance pattern itself already has some zigzag pattern on top of that. Yes, and another thing is for pair instability supernovae, this is also, they are quite remarkable in the sense that at the low mass end, so at 140 solar masses, you basically make no nickel, but this can go up to almost 100 solar masses of nickel that's produced in the explosion. And the other remarkable part is, sorry, this scale here is the explosion energy that can go up from about 4 times 4 beta. So beta stands for named after Hans Bethe, but stands for 10 to 51 ergs. So typical type 1a supernova exploding makes about, or typical supernova makes about 1 Bethe of explosion energy. So these already start high, but at the high mass end, they can make up to 100 Bethes, or 100 times the explosion energy of a normal supernovae. So if anybody of you is familiar with type 1a supernovae, so type 1a supernovae will make about half a solar masses of nickel and 1 Bethe of explosion energy. But this object makes 50 solar masses of nickel and 100 Bethe explosion energy. So it's basically like 100 type 1a supernovae going off in one spot in terms of energy and nucleosynthesis. So that is what makes them so remarkable. So do I have a few minutes? Okay. So so this is now the interesting part, was put this all together. So there was one object found where we, by Lamosse telescope, that had very peculiar pattern, sitting well outside of what is usually observed. So this is actually something that was, discovered by Lamosse, followed up by Subaru telescope to get abundance pattern, and it had really very low abundances of some of these odd charge number elements and some of these immediate ones as well. So that was, as it turned out, a very this is a comparison to the typical part. Typical abundances, X abundance as a function of atomic number, where this really sticks out compared to what is typically seen. But then, interestingly enough, it was also a very good match for this 260 solar mass pair instability supernovae. So this is comparison for other kind of supernovae 10 or 85 solar mass stars. So these were another good matches, but this one really seemed like okay, the nail in the coffin. Okay, this is the match, and we have found now a pair instability supernova progenitor for the first time. People have been looking for this for a long time to find any observational evidence that pair instability supernovae actually exist. They are extremely easy to do in terms of numerical simulation. There are very clear predictions from theory, but there's not really any unique observations that other than this one here that would tell you that they really exist. That many of the supernovae can sometimes explain in different ways, but the abundance pattern fitted very nicely. There's a few things where there's only upper limits, and this was all fantastic. And so the argument would be, okay, this is so this was a POP3 pair instability. So this was one of these very big stars that probably formed very early in the universe. And in this case, it made a lot of metals that we have seen. And if you enrich your gas with lots of metals, you can actually form stars after that very quickly. And this object didn't even have that low metallicity. It had like 100 solar metallicity. And so it probably would have formed also very quickly after that in the second generation, and therefore is in our galaxy for a very long time and the oldest star. So this is where the title comes from. I thought, okay, it must have formed quickly in the second generation of something that was formed very early. And as I said as well earlier, the direct descendants of the direct first stars we haven't seen yet at all. So this would be our best guess of things being the oldest. Now then there was one of my former collaborator or postdoc I've been working with said, well, but I have different models, and this is his student made these models of rotating models that included stellar rotation in the nucleosynthesis, and they found things. So this is the chi-squared, how well it matches, and they found models with rotation that actually fitted equally well. This was just one of the parameters we hadn't looked at before for these low mass things, and so they were able to do this either for zero metallicity or even for some metal-rich stars. So this is 1,000 solar metallicity, where he gets very good matches. So maybe our was a little bit too soon. So we maybe need more abundance patterns, more abundance measurements that will really nail this down in order to to be more sure. So we need more measurement, more observations. This is probably good for people here in the audience. They're telling yes, we need more. But then there was a preprint. I was sent a copy just last week, and they did actually a lot more measurements already on this one, and they found some changes. So thing was this paper I showed you at the beginning, and they now had some new abundances with high resolution tech, and they also found particular carbon and filled in some of the elements of odd charge number. Also, this one is a pretty bad one, the strontium, that shouldn't be there from pair instability. And when they did this, they found a match of something that's maybe only 11 solar masses, has a much better match with this enhanced abundance pattern that they now have with new determinations. So that maybe, this may be finally killing this as an idea of being, if this is confirmed, but I have no reason to doubt that their measurements are better, and because they filled in things that were only upper limits before. And so with that, it also means that the price is still out there for taking observations and finding another object that has the properties that match for pair instability. So I think with that I should conclude. So yes, we should expect to find this kind of not too intermediate low metallicity 100 solar composition metallicity stars as things to look for. They're a needle in the haystack, because there will be a lot more stars of similar composition that have different origins, but this is where I would be looking for to find evidence for pair instability from first generation of stars. So, but unfortunately, there's a few degrees of freedom in the modeling that we have taken into account, that we need to build bigger databases of nucleosynthesis models as well for the matching. But if you find such a star, it should be the good candidate for the oldest stars in the universe that we know. And this is, when we are after that, this is what we should be looking for, I think. Thank you.
Well, thank you very much, Alexander. It's a very exciting field, obviously, especially with all the new data, as you've shown. We have an online audience, and we have an audience here. I'd ask the online audience, if they have questions, to write a message to us, and I'll take questions now from the floor, from the audience here. First one. Norbert Christlieb.
Thank you. So if I understand it correctly, we need to search not only for the odd-even pattern in the pair instability supernova descendants, but we also need a strong upper limit for carbon, right? Because they don't produce any carbon.
Well, in this case, it was the carbon that they were measuring for the first time that was a killer for the pair instability, because it wouldn't make it. So the full pairs, this model could not make as much carbon, so it would not be a good match. So anything that you find that can't be easily made by the pair instability, obviously is a killer for the star being a pair instability. If you have only one element, you can match it. If you have two elements, maybe. But if you have lots of things that disagree, then it gives you much tighter constraints on whether.
Mm-hmm.
But it's not necessarily carbon. So if you had to fill in, if you had lots of sodium at a very high level, that would also be almost impossible to make by pair instability. So it's not the only thing that necessarily kills it. There's many other ways. So once you get these strong deviations from that pattern, this is what kills it. And carbon is one of the things that is not predicted by the model.
And second question, if I may. So how can rotating stars produce the odd-even pattern? What's the physical mechanism for that? You showed this match of the rotating stars.
It was a pattern. It was not just the odd-even pattern, but it was models where So these were very parametric models that didn't do full 3D hydro, and they assumed that you have a mass cut and you only check the outer layer. So they took this to an extreme, saying playing more with the parameters in different ways with what you can do in the mixing between the core and the envelope when you eject it. And then you eject only this some of this helium layer with a little bit of admixture, and there you had production of these intermediate elements and not too much of these odd elements in there yet. So that would just match.
So in other words, it's a little bit contrived.
Yeah, I think they had more degrees of freedom in their matching that they took advantage of. But they said, well, if this was the case, and then they could reproduce it. But these are not, what they did is not absolutely unreasonable that something like this might happen. It's just not in the same way modeled from first principles forward, but instead it's trying to see, okay, if we had models where the supernova asymmetries were in this way that you get this kind of mixing, then it would be a match as well. So you're not required to have a pair instability as the only possible solution.
Okay, we have one question from the online audience. So Hans Zinnecker is asking, can you explain what is meant by semi-convection?
It's a certain kind of instability that can happen when you have a stabilizing composition gradient and destabilizing temperature gradient. So it's a typical textbook. For example, you can read it up in Kippenhahn, Weigert.
Oh, okay. I'll pass that on to Hans.
Okay.
I guess you're there,
Yeah,
Hans. If
yeah,
you
I
want
had
to
a,
come
I had
back for
a,
that.
there was
Write
just
it
a
down.
question.
Greetings to you,
Can you hear me?
Hans.
Can you hear me?
Well, I guess we're a little bit behind time. Is there another question?
Just a quick
One more question.
quick question. I mean,
I see
we know that globular
That's long
clusters,
row.
globular clusters have stars of metallicity -2
Thank you very much.
decks.
I always have a
So-
conceptual difficulty
so-
in understanding how the first stars form and how you form the next generation of stars from material that is only enriched by one supernova. So if I imagine the universe today, you form several stars at the same time, and then maybe you have several supernovae that go off, maybe before you form the second generation. How does that picture kind of fits into these searches?
Well, I mean, we have one halo, and yes, I agree that some of the more modern simulations seem to suggest that you may have 2 or 3 of these stars forming together as a multiple star system inside that. That's also a more recent outcome. But if one of them is a pair instability supernovae and the others are somewhat less massive, do not make pair instability, then probably the nucleosynthesis yield of that one would dominate, and you would see preferentially that signal. I think it can make one can make it make sense and make it work. That it so if the other ones, if you have one that is 150 and there's 2 or 3 others that are 80 solar masses and they make black holes instead and don't yield enough nucleosynthesis, then you don't seem to be convinced. One of them explodes, makes 100 solar masses of metals, and the other ones make black holes and eject. Maybe if they're lucky, one solar mass of metal still escapes. And it may mostly be oxygen carbon, so it wouldn't really change the resulting pattern. So you have to have the other stars either produce a lot of polluting metals that fill in the gaps, say the odd Z elements, to destroy the pattern. Yeah. What do you have in mind? Why would it not work? Yes. Well, the core columns don't give you that much carbon. So yes, I mean, yes. So the idea here was to find a unique pattern. We want to have a single object doing the entire pattern, or at least dominating the pattern, because once you allow for 2 stars or 3 stars contributing to the components, what people have done in part where they said, well, some of these patterns that look a little bit like pair instability, maybe it's a normal supernova and a type 1a supernova. So this you can do. You have more degrees of freedom. If this is what you have in mind, and we have played with that as well. But strongest evidence that which has the fewest degrees of freedom you would get from if you really can match the single pattern, a unique single pattern is matching to the pattern that you see. That, yeah. But yes, you can probably compose a similar pattern, maybe of two different things, but then you have so many more degrees of freedom that the evidence is less in terms of statistical analysis.
Okay, fascinating discussion. Maybe we can continue at dinner tonight. That's one of the two announcements, dinner tonight, which will be at 1900 Dorfschenker, just across the road in the Neuenheimer Platz, Neuenheimer Platz, yeah, I think, Marktplatz, yeah, Neuenheimer Marktplatz. But before that, we have a students meeting and Kirill Maltsev. Just show yourself, Kirill. Please meet Kirill at the bottom. Afterwards, anybody who wants to go for students meeting directly after the colloquium. And then another announcement is next week's colloquium. Also going to be talking a bit about supernovae. So Robert Fisher will be, who is a visiting professor here at HITS, will be telling us about white dwarf supernovae. So that goes together quite well with the talk today, I think. So with that, I think we'd like to thank Alexander once again for this insight and this very exciting and ongoing topic, as it looks like, both observationally and theoretically. Thank you very much, Alexander.
Thank you very much for having me. It was my pleasure.